This is the AP Statistics Chapter 7 Test Review. Each boldface number is the value of either a parameter or a statistic. In each case, state which it is using the appropriate notation to describe the number. On a New York to Denver flight, 8% of the 125 passengers were selected for a random security screening before boarding. According to the Transportation Security Administration, 10% of passengers at the airport are chosen at random for screening. So for the entire population of all people who are passengers at the airport, the proportion of them who are screened is 10%. So our parameter in this case would be P equals 10% or 0.10. For the statistic, from our sample, we know that the proportion of those people who got checked was 8%. So a P hat in this case would be 8% or 0.08. What happens when you increase the sample size? As the sample size increases, the variability of the data decreases. Also, as the sample size increases, the approximate sampling distribution becomes more normal. So the larger the sample size, the tighter the data is going to be, less variability. So if we have a sample size of 20, it could look like this. But if our sample size is only 100, it's going to be much more narrow. It's going to have less variability. And also, the larger that sample size gets, the more normal the shape of your sampling distribution will become. If you take a sample size of 340 from a given population, for what values of P would it be safe to use a normal approximation to find the sampling distribution of P hat? Now, for this to be normal approximation, remember n times P must be greater than or equal to 10, and n times 1 minus P must be greater than or equal to 10. Since we know that there are 340 people in the sample, we know 340 times P must be greater than or equal to 10. And we know 340 times 1 minus P must be greater than or equal to 10. On both of these, we can just divide by 340. So we know that our P value would have to be greater than 0.029. Over here, when we divide by that 340, we know that 1 minus P must be greater than or equal to 0.029. If we take the 1 to the other side, this is going to give me negative P has to be greater than or equal to 0.029 minus 1, which will give us a negative 0.971. If we divide by a negative 1 to get the P by itself, remember, when you divide by a negative, that is going to switch your inequality sign. So we know that as long as P is greater than 0.029 but less than 0.971, that this would be a normal distribution that we could use. A researcher initially plans to find a simple random sample of size n from a population that has a mean of 50 and a standard deviation of 5. If he were to triple his sample size to 3n, the standard deviation of the sample distribution of the sample mean would be multiplied by, when you are finding the standard deviation, it is the square root of 1 over the sample size. Since this is 3n times larger, we would need to multiply our standard deviation by the square root of 1 over 3n. The central limit theorem is important in statistics because it allows us to use normal probability calculations to answer questions about sample means from many observations, even when that population distribution is not normal. So even if the population isn't normal, because of the central limit theorem, we can still use those normal approximations as long as your sample size is at least 30 or larger. The Internal Net Revenue Service plans to examine a simple random sample of individual federal income tax returns for each state. One variable of interest is the proportion of returns claiming itemized deductions. The total number of tax returns in each state varies from over 15 million in California to about 240,000 in Wyoming. Will the sampling variability of the sample proportions change from state to state if the simple random sample of 200 tax returns is selected in each state? Explain your answer. As long as the sample sizes are the same, the variability should also be the same. The variability only changes if the sample sizes are different. Now for part B, will the sampling variability of the sample proportions change from state to state if the simple random sample is just 1% of the tax returns in the state? Since 1% of the tax returns in California would be a lot more than 1% of the tax returns in Wyoming, because California has a larger population, then these sample sizes would be different. So the variability for California would be smaller than the variability for Wyoming because the sample size is larger. The height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. If 4 women are randomly selected and their heights are measured, then 95% of the observations should occur in what interval? So we know that 95%, if you remember back, 95% of the data should fall within 2 standard deviations of the mean. We know that because the mean population is 64.5, the mean of the samples would also be 64.5. Before we can find our standard deviation for our sample, we first have to check that 10% condition. Since we are taking a sample size of 4 women, there is at least 10 times 4 or 40 women in the entire population, so the 10% condition is met. So now we need to find the standard deviation for our sample. Remember, to find the standard deviation of your sample, you're just going to do the standard deviation of the population divided by the square root of n. We know our sample size is 4, so 2.5 divided by 2 gives me 1.25 for the sample. So if on this bell curve our center is at 64.5 and we know that 95% of the data falls within 2 standard deviations, if one standard deviation is 1.25, then 2 standard deviations would be 2.5. So 2.5 standard deviations, or 2.5 units below the mean, would be 64.5 minus 2.5, which is going to give us 62. And if we do 2 standard deviations above the mean, that will give us 67. So we know that 95% of the data should fall between 62 and 67 inches. According to the government, 24% of American children under the age of 6 live in a household with incomes that are less than the official poverty level. A study of learning in early childhood chooses a simple random sample of 500 children. Find the probability that more than 23% of the sample are from poverty households. Be sure to check that you have used the normal approximation. So first, we know that the mean of our samples will just equal the mean of our proportions from our samples will just equal the proportion from the population, which is 0.24. Now you need to check that 10% condition before you can find the standard deviation. We need to make sure that our sample is less than 10% of the entire population. And if we do 10 times our sample size of 500, this would give us 5,000 children. We can guarantee there's more than 5,000 children in America, so that 10% condition is met. So because the 10% condition is met, we can now find the standard deviation, which is p times 1 minus p all over n, or our probability of success times the probability of failure. In this case, success would be that they are in poverty, failure would be they're not in poverty, over the sample size will give us a standard deviation of 0.019. Now we need to check that we can actually use normal approximations. Remember to do that, you're going to do n times p, and that has to be greater than or equal to 10, and we're going to do n times 1 minus p, and that also has to be greater than or equal to 10. So we have 500 samples. Our probability of success is 24, and that's going to give us 120, which is definitely greater than or equal to 10. And we're going to do 500 times our probability of failure, which in this case is 76%, and that's going to give us 380, which again is greater than or equal to 10. So we are allowed to use our normal approximations. So we are going to use normal approximations with a mean of 0.24 and a standard deviation of 0.019. Now we want to find the probability that our p hat is greater than 0.23. To do this, we're going to have to find our z-score. Remember, z is going to equal x minus mu all over sigma. And we are talking about the mean and the standard deviation of just the sample, not the entire population. That is why you had to find the standard deviation for the sample first. So our x value is 0.23 minus 0.24 all over that 0.019. And this will give us a z-score of negative 0.53. From here, you can look it up at the table, and you're going to find the probability that you have a z-value of less than negative 0.53 to be 0.2981. But we're looking for the probability that z is greater than. Remember, to do greater than, you're going to do 1 minus the probability that it's less than, and we're going to get a probability of about 70%. So there is a 70% chance that more than 23% of the sample will be in a household that is in poverty level. The amount that families pay service providers for cell phones varies quite a bit, but the mean monthly fee is $190 and the standard deviation is 35. The distribution is not normal. Many families pay about $120 for a shared amount of data or about $180 for unlimited, but some pay much more for faster connections and multiple devices. A sample survey asked a simple random sample of 800 families with cell phone plans how much they pay. We're going to let X be the mean amount paid. Explain why we cannot determine the probability the amount of a randomly selected family pays will exceed $175. Since we are only talking about one specific family, not the mean of a sample, then the distribution itself would have to be normal. Since the population distribution tells you it is not normal, we cannot do these calculations. But if we were talking about the mean of our sample of 800, we could do this calculation because it is a sample, not just an individual. So the normal approximations cannot be used in this case. So what are the mean and standard deviation of the sampling distribution? Because we're talking about the sample, we can actually do this now. So remember, the mean of your sample means is just equal to the mean for the entire population, which is 190. Before we can find the standard deviation, we do need to make sure that the 10% condition is met. And if we do 10 times our sample of 800, we are going to get 8,000. There are more than 8,000 families in the United States that have cell phone plans, so the 10% condition is definitely met. So we are able to find the standard deviation for our sample. The standard deviation formula is just the standard deviation of our population divided by the square root of our sample size. And if we do this calculation, we're going to get a standard deviation for the sample of 1.237. What is the shape of the sampling distribution of X bar, and justify your answer? Since our sample size is well over 30, we can say that the shape of our sampling distribution of X bar would be approximately normal because of that central limit theorem. So even though the population distribution is not normal, as long as your sample size is greater than 30, because of that central limit theorem, the sampling distribution will be approximately normal. And we need to find the probability that the average fee paid by the sample families exceeds $187. Now again, because this is the sample of families, not an individual family, we can do these calculations. Remember, we said this is going to be a normal approximation for the sample with a mean of 190 and a standard deviation of 1.237. We're trying to find the probability that the X bar will exceed or be greater than 187. To do this, we are going to find our z-score. So x minus mu sub x bar all over sigma sub x bar. So 187 minus 190 all over that 1.237 is going to give us a z value of negative 2.43. Now we can find the probability that z is less than negative 2.43 by looking that up at your table, and that would give you 0.0075. To find the probability that z is greater than that negative 2.43, you would have to do 1 minus the probability that it is less than, and that's going to give you a probability of 99.25. So there's about a 99% chance that if you take a sample of 800 families, that the mean from that sample will exceed $187.